Hello everyone. I welcome all of you on the massive open online course, and today I will take up crustal melting, Migmatites, granite association and experimental studies. Introduction. Metamorphism, deformation and magmatism are the three main internal processes within the earth. It is known that melts of basaltic compositions are generated in the low velocity zone, also called asthenosphere, which is nearly 70 km under the oceanic crust and 180 km under the continental crust. Other source regions of the basaltic magma are divergent and convergent lithospheric boundaries. Melts of granitic compositions can only be generated in the continental crust. Some dozen mechanisms of magma generation have been proposed by Yoder 1962, but everyone is simply a change of pressure, temperature and composition, unlike a pure phase. A rock melts over a range of pressure and temperature, and the liquid produced on partial melting does not have the same composition as that of the original rock. This is true for both mantle and crustal rocks. The curve showing beginning of melting of a rock is called solidus, and the curve above which the rock system is completely liquid is called liquidus. Melting or partial melting occurs when temperature increase or pressure decrease, or if H2O influx occurs. The effect of these three agents of melting, which are also of metamorphism, can be easily understood with reference to dry and wet solidus curve, S equal to solid, L equal to liquid, of a crystal rock or mantle rock. Material A is below the solidus and is completely solid. By changing any one of the agents, we can perturb the situation so that melting takes place. First, when we increase the temperature without change of pressure, a rock is partially melted, but increase in temperature results into decrease in density of the crustal or mantle rocks. This would result in uplift of the Earth's surface, meaning increase of pressure. But erosion would then decrease the pressure second. Decrease in pressure in a crustal segments, as during crustal thickening, would also cause melting. This is familiarly called decompression melting, exemplified by basaltic eruption, the middle oceanic region, when the point A moves adiabatically, thermally insulated from its surroundings like a plume melting ensure. Melting also takes place when influx of volatiles, mainly H2O, occurs during metamorphism. This would reverse the slope of the solidus. This wet solids or H2O saturated curve is characterized by temperature reduction as pressure increases because of the vapor effect at high pressures. Crustal melting and granitic magmas. The absence of significant volumes of granitic rocks in ocean regions precludes the possibility of granite generation by partial melting of mantle pedotites or subducted oceanic basaltic crust. This absence also precludes the possibility of production of large volume of granitic magma by differentiation of partial basaltic magma, differentiation of parental basaltic magma, because experiments have shown that 100 parts of basaltic magma can give rise to only 5% of granitic magma through fractional crystallization. Granitic rocks of basaltic dimension cannot thus form by fractional crystallization. Again, the efficiency of the process of metasomatism involving addition of silica, alumina, alkalis bearing fluids called icons into the pre-existing crustal rocks and thereby transforming them into granite looking rocks is untenable. This granitization process or metasomatism does not find support from thermodynamics and physicochemical data. Features such as exsolution in alkali feldspar, zoning in plagioclase, an equal volume of quartz alkali feldspar, plagioclase in most granitic rocks do not support metasomatism as a granite forming mechanism. The only mechanism for generation of granitic melts is anastasis or partial melting of crustal rock. The mechanism was proposed by Sagar in 1908 from the field observation in the Finland region where granitic rocks are intimately associated with mixed rock called migmatites. Here, high grade schist gradually developed pots, organs, veins and folded layers of granitic material which when developed on large amount is found to contain relict of the schist. Migmatites. Migmatites term was introduced by Sagar in 1908. The migmatites are coarse grained, heterogeneous and megascopically composite rocks comprising portion of magmatic or magmatic looking rocks and portion of metamorphic rocks. The magmatic or magmatitic likes portion contain quartz and feldspar and is this granitic is composition and light color. It is called leucosome or neosomes. The metamorphic portion is dark colored and contain biotite and other ferromagnesium minerals such as garnet, cordierite, gaderite with little quartz and some plagioclase. This portion is called melanosome. Its minerals show preferred dimensional orientation unlike those of leucosomes. Types of migmatites. The parent rocks, whether metapelites, schist or gneisses or metagravax, designated paleosome, has a variety of relationship with its melted granitic fraction called neosome or leucosome. On melting, the paleosome changes its composition, which is now observed as restites, unmelted components, and it is designated melanosome. If it's all happens in suit, then melanosome plus leucosome equal to paleosome, and one can determine the parent composition from the chemistry, mineralogy and volume relationship of the melanosome and its leucosome. The mixing of the paleosomes and melanosomes give rise to several types of migmatites depending on the structure of these rocks. If the dark and light layers occur in nearly planar bands of a few centimeter or even meters in thickness, these migmatites are called banded gneiss or venites, veins of granite alternating with dark bands, or stomalites if leucosome appears in layers parallel to S surface, and in veinlets the migmatites is called dectonites. If these bands show folds of various dimension, they are called folded migmatites. If the dark colored portions has the appearance of breccia embedded with the leucosome, the migmatite is called agmites. If the dark portion is on a vanishing stage and is recognized by dark celeron or streaks without the granitic portion leucosome, this migmatite is called nubulites. Mineralogy and phases. The migmatites are divides of muscovites plus quartz parengensis and are found in high-grade metamorphic terrain in association with granitic bodies. This type of geological occurrence is reported from all over the world. Clearly, the migmatites belong to upper amphibolite phases where muscovite is no more stable in quartz-bearing rocks. Although migmatites are in the upper amphibolite phases rocks, even in gammalite phases, and are associated with granites, but migmatites rocks show no partial relation to granitic bodies where granite is absent. Migmatites are abundant, and where granite is present, migmatites are not necessarily present in its vicinity. Slederholm in 1907, followed by other geologists, suggested that the leucosome of migmatites was formed by partial melting of pre-existing meta sediments, and this mechanism is called anataxis or partial melting by Slederholm. Experimental work and origin of migmatites and granites. Anataxis or anatactic process for the origin of migmatites and granites have been shown by experimental melting of rocks, namely shell, gravax, schist and gneiss. Anataxis is the most important process affecting the earth crust. As stated earlier, it occurs in the deep crust, particularly in areas along convergent plate margin and in collision mountain belts recorded by extensive areas of migmatites and gammalite terrain associated with granitic rocks. The extraction and ascent of the granitic melts and obviously lead to the redistribution of elements in the crust. Furthermore, the nature of the source and the condition under which anataxis occur determine the character of the resulting melts. This has been demonstrated by the laboratory experiments on melting of rocks. The first experiment was done by Peter Wiley in 1952, who reported a melt of granitic composition when cell was subjected to melting in hydrothermal experiment. Subsequently, Tuttle and Woman in 1968 performed melting experiments on granite system, quartz, alkali feldspar, sodic plesioclase and water system, that is quartz, orthoclase, albite, water. They experimented at different pressure, that is water pressure, and found that granite melting begins nearly 650 degrees centigrade. Eutectic is located between quartz and alkali feldspar, while no eutectic occurs between two alkali feldspar, because of solid solution between them. Just like in plagioclase feldspar, one can think this triangular diagram as a combination of the two composition system, namely quartz albite, quartz orthoclase and albite orthoclase system. In this three-phase system, quartz orthoclase albite with water, there occurs a ternary minimum, that is also known as TM or cotectic minimum, at which the last liquid on fractional crystallization tend to reach. The temperature minimum is found to shift towards albite corner with increasing water pressure. See Tuttle and Warman in 1958. When PS2O increases to about 4 kilobar, the cotectic minimum was found to become ternary eutectic. This will be the composition of the first melt from melting of any niches at 4 kilobar pressure. At this point, quartz albite orthoclase will coexist with melts and vapor. The temperature eutectic is also found to shift towards albite corner with increase of pressure, as shown by further melting experiments by Lutz et al. In 1964. These experimental results were applied to the origin of granitic rocks by Tuttle and his co-workers. These authors plotted normative quartz albite orthoclase of the available analysis of granites and rhyolites. These plots, when viewed in light of the experiments on granites system, demonstrate that first, the granites are a product of crystallization from a melt, since the felsic portion of most granites correspond to the ternary minimum or cotectic minimum, also called temperature minimum, and to the ternary eutectic. Second, the rhyolite also showed that quartz albite orthoclase maxima near the cotectic minimum and thus coincide with the maxima of granites. This evidence rejects the hypothesis of metasomatism and support that the granitic rocks are produced from crystallization of melts. Third, the composition of the first melt formed upon heating of any composition in the granite system, a mixture of quartz albite orthoclase phases would correspond to the composition of ternary eutectic at the specific pressure. This is the consequence of the fact that minerals of natural granites are always in equilibrium, hence ternary eutectic crystallization occurred and the T eutectic composition is pressure dependent. Temperature eutectic shifts towards albite corner with increasing pressure. The melting experiments on the granite system clearly show that dry granite solids has a positive slope while wet solids has a negative slope. This helps us to understand as to why granites are most abundant plutonic rocks while basalts and not rhyolites are most abundant volcanic rocks. In the case of dry melts, positive slopes, more heat is needed to produce dry magma nearly 1000 degrees centigrade, which therefore originated deep within the crust. When this dry granites melt rises, it is erupted as rhyolites and the volcanic products. The wet melts negative slope, although produced at low temperature, nearly 650 to 700 degrees centigrade at shallower depth, nearly 15 to 20 kilometer within the earth, cannot rise far before crystallization. That means that wet melt will never be erupted as acid volcanics. On the contrary, the hot water under saturated silica magma may be able to ascend to much higher crustal levels. This melt, if tonalitic in composition, is likely to produce granites by fractionation, but leaving the lower crust anhydrous dominantly of gamma-lites. When we want to understand the experimental results on granite melting in the framework of orogenesis and regional metamorphism, this shows granite melting curves with different H2O content or ratio of P water upon P loads. A wet melting curves of granite is saturated with H2O and has P water equal to P load, whereas the dry melting curves of granite has P water equal to 0, no water in the system. A series of melting curves for condition with H2O equal to 6%, 4% and 2% are also shown. A typical geotherm ABCDE is met to pass through the triple point of Al2SiO5. Exact position is not important. In this diagram, a series of adiabates A, B, B, etc. are constructed on the assumption that the adiabatic decrease in temperature with decreasing pressure is 10 degrees centigrade per kilometer. Exact value unimportant. Now imagine that a rock of a particular water content moves along the geotherm ABCDE and crosses the granite melting curves. Appreciate to its water content begins to melt location X. The liquid formed by partial melting along grain boundaries starts to collect together, and by then temperature has also increased slightly due to negative density and buoyancy. This collected magma will rise approximately along an adiabates with its temperature decreasing as the P load decreases until it hits the melting curve again. If the liquid is not saturated with H2O, then it can cross the appropriate melting curve by partially crystallizing. Consequently, the remaining liquid becomes enriched and the crystallized liquid is left behind. The melt can go on rising until P water equal to P load, and thus the granite melt reaches the wet melting curves. The body continue to crystallize at this point until it is completely solid, releasing excess water as pegmatitic fluids of lower melting points. The other alternative is that P water more than P load and the liquid would escape as a volcano to crystallize as a glass. The distance a melt can rise is constrained by slope of wet melting curve. Granite melts formed in a region where P water equal to P load can rise only a little away before it must solidify A dash. As the P water upon P load ratio becomes less and less, granitic liquids can rise further and can reach near the surface before solidifying. Such liquid should be dry melts. Curve E dash as stated already. In short, the higher a granite rise, the deeper it must have been formed. Tuttle and Warman experiments conclusively showed that granites are formed from melt, but whether the melts generated from hydrous melting of sediments or their metamorphic equivalents could also be developed granites is not suggested by these experiments performed in the simple granite system quartz albite orthoclase water system. It is a weakness of these experiments that their results cannot be applied to calc alkaline granites such as granodiorites, tonalites, etc. Therefore, Winkler and his co-workers did experiments on quartz orthoclase albite anorthite water system as well as on the melting of gneisses and metasediments. Here all the four components excluding water being an axis phase occupying the four corners of a tetrahedron. The tetrahedron space is divisible into two bounding surfaces shown as planes which divide the tetrahedron into three regions. The plane E1, E2, E3 separates liquids, melts, precipitating feldspar, the region in the front of the planes, from those liquids that precipitates quartz behind the plane. The plane E4, E5, P, E6 divides the feldspar regions into two by separating liquids that precipitates plagioclase above the plane from those liquids that precipitate alkali feldspar below the planes. The line of intersection of P E5 is a cotectic line, and from liquids on this line simultaneously crystallization of quartz, plagioclase, alkali feldspar takes place. Winkler and his co-worker found that first melt generated by quartz albite orthoclase anorthite water system and also by gneissic rocks was granitic in composition. With further heating, the melt becomes granodioritic and finally tonalitic. This compositional change of the melt from granite to granodiorite to tonalite transhemites along P to E5 occurred within 35 degrees centigrade. This is a significant result as the given sequence of melting is the reverse sequence of fractional crystallization. The experiments further suggest that higher the anorthite content in the parent rocks, the melting temperature will be higher and will be richer in quartz with increasing pressure. The results shown in above figure demonstrate that as the proportion of anorthite in the melt becomes larger, the eutectic shifts towards quartz and feldspar. See position of dots on the cotectic lines. Second, the first melt should be close to the quartz albite orthoclase eutectic and should contain very little anorthite. Third, as the temperature increases, the melt becomes gradually richer in calcium and hence granodiorites to tonalites composition are obtained with increasing melting temperature of rocks. From these experiments, it is obvious that a melt with higher calcium will crystallize plagioclase and the ultimate residual liquids would be rich in quartz and orthoclase. This explains the formation of tonalites, granodiorites, granite in close association. The granitic melts formed during high-grade regional metamorphism are the result of increased temperature, which is associated with rock deformation or crustal thickening by structural duplication. In this process, the mechanical work is transformed into sufficient thermal energy, simple compression or squeezing of rocks at depth due to weight of overlying material would result into temperature increment, which together with friction would cause melting at thus elevated temperatures. This is common during orogenesis or continental collision or plate tectonics. When crustal rocks, a tonolitic gneiss, amphibolites, peltic schist undergo partial melting or anastasis, the first melt forms along grain boundaries. This melt, although minute, is of granitic composition. Only when the melting temperature rises just 10 or 20 degree above the solidus, the small bulbs of granitic melts segregates as veins or layers within the paranesis undergoing melting. This situation will produce venites and bended knees, that is Migmatites. If sufficient water is present into bringing about partial melting of the rock, we may have Agmites type Migmatites in which broken fragments of darker knees are surrounded by more or less homogeneous granitic material. It is estimated that about less than 50% melt or more could produce nubulites structure in which only the dark celeron are recognizable in an otherwise granitic composition. The granitic melts, because of lower density, will migrate upwards as the isolated blebs comes together and form larger body of melts. The larger granitic melts begin less dense than its surroundings will tend to move upward as a diaperic bodies. Numerical modeling by Gour et al. In 1989, who looks into account crustal melting of the region of thickened crust so that a significant amount of melting take place when heat influx is more than 30 according to their calculation, when Qm is equal to 40 mW per square. Melting begin at 10 million years after thrusting or a structural duplication. The amount of melt generated increases rapidly during the first 20 million years and thereafter 60 million years after. Melting dimension to nil. When large volumes of melts are formed during anastasis favored by excess water, low anorthite content of plesioclase and suitable temperature, these melts may accumulate. This anatactic melt of granite or granodiorite composition may crystallize at same depth at which they originated. This is because a decrease of pressure when the magma rises would rise the solidus temperatures and the melt will solidify at once as it begin to rise. Such granites are octothonous granite of H. H. Reed 1957. All these granites are S-type of granites of Chappell and White in 1975, in contrast to I-type granites formed by fractional crystallization of a basaltic magma. If the magma had temperature higher than its solidus temperature, it will rise up, and these granites are shallow seated plutons, allochthonous, and in extreme case the melt may come upon as rhyolites because the liquidus has a negative slope and the melts will move towards lower temperature as its rise along the liquidus. Additional experiments by Winkler and his associates have also shown that granite melts can also originate from orthoclase-free quartz, plagioclase, biotite, muscovite schist. Potash feldspar component in the melt will be diverted from the muscovite and later on increased heating from biotite according to the following reaction. The reaction is muscovite plus quartz give rise to sillimanite plus potash feldspar plus water. Second reaction, biotite plus sillimanite plus quartz give rise to cordierite and or granite and or garnet plus potash feldspar component of melt plus water. Third reaction, biotite plus quartz give rise to gaderite or hypersthene plus potash feldspar plus water. And for tonolitic or intermediate composition rocks, the reaction hornblende plus quartz give rise to orthopyroxene plus clinopyroxene plus plagioclase plus water is important because dehydration melting of hornblende biotite niches would also produce tonolitic melt. It is for this reaction that restites melanosomes after the release of quartzo-feldspathic melts would becomes darker and contain biotite, gaderite or hypersthene, cordierite, garnet, sillimanite and opaques with or without quartz and plagioclase. These experimental results support the field observation of Selderholm and other following him on the origin of granite and migmatites, establishing a link between migmatites, granites and gamulites or charnockite. Petno 1989 suggested that muscovite dehydration melting is like to be the major melting producing step in the evolution of many orogeny and is particularly important in the metapelites components of the supracrustal succession in orogeny. Without any ingress of H2O rich metamorphic volatiles phase, the amount of melt produced is generally limited by the amount of muscovite in protolith. When the rock cool or are brought near the surface, back reaction would occur whereby the water would be promotes a near melting in the adjacent rocks under appropriate condition. Thomson in 2001 transport a melt out of the source region takes water, which has the consequence for the evolution of anhydrous lower crust and hydration reaction in the upper crust. Once the transported H2O is released on crystallization of the melt. Dehydration melting is important during high and ultra high temperature metamorphism called UST metamorphism, when underplated basaltic magma heats up and crustal base tonolitic magma can be generated. The hot water undersaturated felsic magma of tonolitic composition may be able to ascend to much higher crustal level. This melt is likely to produce granites by two ways. First, fractional crystallization of tonolitic magma produces granodiorites and granites. Second, leapfrog effects when the hot tonolitic magma carries fluids along and ascends upwards, it would cause partial melting in the fertile mid crust, forming water rich, less mobile granites magma. This phenomena of smelting at lower and middle crustal depth by thermal effect of ascending magma is called petrological leapfrog effects. In the absence of water, rock would melt at very high temperature, but the OH bearing minerals like biotite, hornblende may supply water on their decomposition, and thus granitic melts may form at higher temperature if rocks are devoid of free water. Brown and Phi, 1970. Thank you very much.